All right, let's get right into it and break something down that seems, well, kind of complex. Okay, so take a look at this. What we have here are two liquids that are completely clear, right? You can see right through them. But then you mix them together and bam! Out of nowhere, this bright yellow solid just appears. It really does look like a magic trick, but I promise you this is 100% chemistry. And that's the big question for us today. How in the world does that happen? I mean, where does that solid stuff even come from? To figure this out, we're going to have to take a journey from the stuff we can see with our own eyes all the way down to the invisible world of molecules. So yeah, to solve this little puzzle, we've got to zoom way, way in. We need to see what's actually going on inside the water itself. And our very first clue is a process called dissociation. It's all about what happens when certain things, like regular old table salt, just dissolve in water. So what is dissociation? Well, think of it this way. An ionic compound, it's kind of like a couple showing up to a party together. The second they walk through the door, which is the water, they just split up and go mingle with everybody else. They were always two separate parts. They were just, held together. Dissociation is just that separation. And this picture shows it perfectly. See all those little red and white water molecules? They're like the crowd at the party. They just swarm around the bigger sodium and chloride ions and literally pull them apart from each other. So each ion gets its own little group of water molecules to hang out with. Now, this is how chemists write that down in shorthand. It basically says solid sodium chloride, that's what the little S means. When you put it in water, it becomes a sodium ion and a chloride ion. And that little AQ you see, that just means aqueous, which is a fancy way of saying they're dissolved and floating around in the water. So one single unit becomes two separate things just drifting around. Okay, so that makes sense for stuff that's already made of ions. But what about things that aren't? What happens if you dissolve a molecule that doesn't have any ions in it to begin with? And this brings us to a really important difference. Dissociation, what we just talked about, is just separating ions that are already there. But ionization, that's a whole different ballgame. That's about creating brand new ions from a molecule that didn't have any before. So with ionization, the water itself is so powerful, it doesn't just pull things apart. It actually breaks a molecule, creating ions where there weren't any before. It's not just separating that couple at the party. It's more like the water convinces one person to give their hat to someone else, and in doing so, creates a whole new situation. A classic example of this is hydrogen chloride. It's a molecule, not an ionic compound. But when it gets into water, the water molecule literally rips the hydrogen right off of the chlorine. And what you're left with is a chloride ion and this new thing called a hydronium ion. And just like that, you've made ions out of thin air.
All right, so now we've got our two key ideas down, dissociation and ionization. And with those in our back pocket, we can finally go back and figure out the mystery of our yellow solid.
So let's put it all together. Before we mix anything, we've got two separate beakers. Each one has a clear liquid, but really, it's a soup of ions that have dissociated and are just swimming around. In one beaker, you've got cadmium and nitrate ions. In the other, you've got ammonium and sulfide ions. They're all just at their own separate parties, mingling. And now, for the magic moment, we pour one beaker into the other, and we combine the parties. Almost instantly, the cadmium ions and the sulfide ions see each other across the room, and the attraction between them is so strong, way, way stronger than their attraction to the water molecules, that they just snap together. And when they do, they form cadmium sulfide. But here's the kicker. This new compound is insoluble. It can't stay dissolved, so it has to crash out of the solution as that amazing yellow solid we saw from the start. And this quote just sums it all up perfectly. This whole reaction, which we call precipitation, it's basically a competition. It all just comes down to who's more attractive. Are the ions more attracted to the water, or are they more attracted to each other? If of each other, boom, they pair up and form a solid. Now, what's so cool about this is that chemists don't just have to guess which ions are going to pair up. They actually have a kind of cheat sheet that helps them predict if a solid or a precipitate is going to form. These are kind of like the rules of the road. For instance, the first rule tells you that pretty much anything you pair up with sodium or potassium is going to stay dissolved. No problem. But look at that third rule. Most sulfides are insoluble. And that's exactly why our cadmium sulfide appeared. It was just following the rules. But wait, what about those other ions from our experiment? The ammonium and the nitrate? Well, they didn't do anything. They just kind of floated around and watched the whole thing happen. In chemistry, we have a great name for them. spectator ions. They're at the party, but they're just watching from the sidelines. And since those spectator ions aren't really part of the action, chemists like to simplify the equation to just show what's important. It's a pretty simple process, really. You write everything out, you find the spectators on both sides, you cross them out, and what's left is the real story, the net ionic equation. And this is what you're left with. See how clean that is? This is for a similar reaction, but all the clutter is just gone. This tells you the simple truth of what happened. Zinc ions met sulfide ions, and they made solid zinc sulfide. That's it. That's the whole story. So, what started out looking like a magic trick is really just an invisible dance going on, with rules you can actually predict. This is how things like water softeners work, or how incredible cave formations get built over thousands of years. It kind of makes you wonder, right? What other magic that we see every day is just chemistry, waiting for us to zoom in and see what's really going on?